So your first case study quiz is from section 1.6. There's not a lecture for 1.6. I just thought I would do some examples that you'll see on that quiz. Again, there's a homework you can do if you want to practice, but it's not for a grade. It's just for you to practice. And it's just going to be applications. So it's just going to be like a grab bag of things that we can use what we've learned to do. Yeah. What? Yes. I can change that, but yeah, I think it's better because you get 9 attempts, really. You get 9 tries at each problem because you can hit the similar exercise twice, and you get 3 tries at each iteration. So I think that's enough. If you're doing 9 attempts, I think maybe you should come see me before you go on and do the 10th attempt. Okay, come see me and talk to me about it. But the quiz, you just get 1 attempt. You're going to upload your work just like you've done on the other ones. Okay. Yeah. No, but they will be on the final exam. So it's not on the first test. It's related to the first test, but I think doing them takes too long. Like it would make your test too long. But I am going to put them on the final exam because I don't really care how long that one is. Okay.
You don't have to say this anymore. There.
That's right. I don't have to see anymore. That's right. I just turn my email off, you know. But I mean, once you know how to do them, they don't really take that long. But there are some on the final exam. So it's not like you can't. It's not like you don't have to do them. It's just I kind of separated them out from the regular tests. But the final exam, the whole math center gets turned into testing. So there's a lot more room. There's a lot more. You know, we're not tied for space in the math center too much. Okay, so I don't. You know, if it takes you a little bit longer to do the final, then I'm okay with that. And I want to test you on these. I do want to test you on these, but no. Final's not timed. Yeah, I mean, it shouldn't take you 3 hours. The only time limit, I did put a time limit on those just so you're not in there all day. You know, I just don't think. I mean, it shouldn't take you that long. It should take you about an hour to an hour and a half. So I gave you like double time. Okay, I gave you double time. It would take me about 30 minutes. And you have 3 hours. So, I mean, I think that's enough time. So it's like an untimed test. But if you're just sitting there forever, I mean, you know. If you don't know it, then, yeah, I mean, it could take you 100 hours. You still wouldn't get it, right? So, I mean, I don't know. Okay. So, first problem, since suppose Canada, Mexico, or the United States are trading among themselves and only themselves. So this is just a hypothetical, okay? Canada exports 40% of its goods to Mexico, 30% to the U.S., and retains the rest. Mexico exports 30% of its goods to Canada, 20% to the U.S., and retains the rest. Finally, the U.S. exports 40% of its goods to Canada, 20% to Mexico, and retains the rest. If the dollar value of the USA's output is 60 billion US dollars, what is the value of Canada's and Mexico's output in billions of US dollars? We're going to round to 2 decimal places. This is in billions of dollars to 2 decimal places. Okay, so I think it makes sense to draw a diagram. From the diagram, we're going to make a table. With the table, we're going to make a matrix. Okay. Well, actually, with the table, we're going to come up with equations, and with the equations, we'll make a matrix. Yeah, but not. They may not be exactly these. Okay, so you'll see. So we have Canada, Mexico, in the U.S. So Canada exports 40% of its goods to Mexico. So that's Canadian bacon and moose hats, things like that. 30% to the U.S. and retains the rest. So what is the rest? Be 30%. So I'm just going to do this. So 30% stays inside. All right, Mexico exports 30% to Canada. %20 to the U.S. and retains the rest. What would the rest be? 50% or 0.5? The U.S. exports 40% to Canada. %20 to Mexico. And retains the rest, so that would be 40%. They have different exports, right? So they're just buying and selling each other. They're selling their exports. They're buying someone else's exports. Okay. All right. So that's how it would look. So let's see. So let's look at Canada's. Let's just do output. Let's say output. So we've got Canada, Mexico, USA. We'll say output from. And then input to. Canada, Mexico, USA. So Canada sends 40% to Mexico, 30% to the USA, and keeps 30% to itself. And when you add up the column, it needs to add up to 100%. It needs to add up to be 1. Okay. Then Mexico, 30% to Canada. It keeps 50% for itself and sends 20% to the U.S. And then the U.S. sends 40% to Canada, 20% to Mexico, and it keeps 40%. So it would be what we want we want output equations, okay? Because the question was about output, and we'd like our equations to be in rows, so that's why we set it up that way.
So you want the output at the top so that the x's are the different.
Yes. So what this says, we'll use CM and U, okay, for the variables. The first row says that 0.3 C plus 0.3 M plus 0.4 U equals C. Same C. That's their output, their total output.
Oh, equals Canada. The total input of Canada equals output of Canada, Mexico, this and that.
Yes.
So that C and that C over there are equal.
Yes. So Mexico's sending 30% to Canada, and USA's sending 40% to Canada. This is Canada's total.
See, I would have thought it would have been like 30% of that total too.
They're keeping 30% of their own, and then this is what they're getting from the other countries. Yeah. So yeah, these are input equations, and the variables are the outputs, which is what we want to find. So I think I said that wrong a minute ago. We're looking for we're given USA's output. We want the others, and the variables are the outputs for each. So what we're going to do is set all these equal to 0. So we don't want variables on the right side. We want all the variables on the left. So if I subtract C, I get this equation. So there's one. There's one equation that we're going to use in our system. We'll use a different color here. We'll use red. Let's do the second row. 0.4 C plus 0.5 M plus 0.2 U equals M. So that's Mexico's input, right? That's their imports. So we subtract M. That turns that into negative 0.5, right? So that's our second equation. And then the last one, 0.3, 0.2, 0.4. Subtract U. Sorry? Question?
I thought it was 40%. It's 40% to Canada, 20% to Mexico, and 40%, right?
Yeah.
That adds up to 9 or 90%.
We're looking at, so this is USA's exports, right? But this is what the USA's bringing in. They're imports, right? So 30% of Canada's exports and 20% of Mexico's exports, and they're keeping 40% of their own. The columns have to add up to be 100%. The rows don't. The rows don't have to add up to be 100%. Okay. All right, so this was, if we subtract u, we get negative 0.6 u equals 0. So this is our last equation. We're going to put all that in a matrix. Let's try to solve it. Okay, so we're going to have a matrix. Variables are going to be C, M, and U, augmented with 0. So negative 0.7, 0.3, 0.4. There we go. Right. I don't expect you to do this by hand. Right. Exactly. Yeah, I mean, I want you to use technology, but you got to do a lot of stuff to get it to this point, right? So that, I mean, that's what I'm looking for. Do you understand the setup? All right, I'm going to pick a different matrix. Let's call it B. It's 3 by 4. This one wouldn't be bad to row reduce. First thing I would do is I'd multiply every row by 10. And then just start row reducing it, yeah. The solution would be the same no matter if you multiply by, each row by 10 or not. Okay, so now no. The solution C, M, and U will be the same even if you multiply. You get the same answer. Otherwise, we couldn't. Multiply by a constant. Right? It would change the solutions. All right, this is what we get. All right. So do we have a free variable? Yes. So U is the free variable, right? So we'll call this X. X is going to be the outputs of Canada, Mexico, and the United States. So this would be 26 over 23 U, 30 over 23 U, and U. And the problem says if the total dollar value of USA's output is 60 billion US dollars, what's the value of Canada and Mexico's output in billions of dollars? So if we know the United States, can we get the other ones? Yeah. So we're going to say let U be 60. So X is going to be approximately, we're going to round these to 2 decimal places. So 26 divided by 23 times 60. 67.83. And then 30 over 23 times 60. 78.26. So that's Canada, Mexico, United States. In billions of dollars. Everybody good?
That only works if the three variables in the United States.
Yeah. Because that column didn't have a leading one. Yeah, and it gave us. Yeah, it knew that was free variable. So. Right, the next one's network flow. So network flow. This is a very interesting problem. You know, it's presented as if these are roads and intersections, and the flow is traffic. But you can imagine it could be computer networks, and the flow could be data, ones and zeros. It could be a lot of different things, right? It could be foot traffic. It could be a lot of things. So mathematicians call this diagram a graph. Really fancy name. So this diagram is called a graph, and there's a whole branch of mathematics called graph theory, where you study these kind of network systems, try to find quickest path, shortest path, paths of least resistance, and things like that. You know, we like to analyze things like if this is a city, you know, where would you put the fire station? Things like that. You know, how do you figure that out? You know, so if you study math further, you can get into that. Interesting stuff. So we have 4 intersections. We have 5 variables, and the variables represent the traffic flow between the intersections. Okay. So we want to first solve the system for each variable, for each x1, x2, x3, x4, and x5. Okay. So we have to come up with equations that we can solve these for. So the equations are going to come out of the intersections. So we're going to assume that the number of cars that go into an intersection equals the number of cars that come out, that they don't disappear into another dimension or something. Okay, so this is like the conservation of traffic through an intersection. Okay, it's like a conservation law, right? We don't create new cars, and cars are not destroyed in the intersection. Okay, so the first intersect, we'll call this A. So for intersection A, we have 400 going in, x2 is going in, x1 is coming out. So x1 is equal to x2 plus 400. Right? And there's an equation. we don't like it in this form, right? Well, if we want to put this in a matrix, we want all the variables on the left and the constants on the right. So it's like standard form, right? So we want to just move that x2 over, and then we can put that in a matrix when we get ready. Let's call this one B. So what's going in? X1 and X3. It's got to equal what comes out. X4 plus 600. And again, we want to move the variables all to the left. Constants on the right. The arrows tell you which way it's going, right? So you need the arrows. So in B, X1 is going in and X3 is going in, and X4 is coming out, and 600 is coming out. So what goes in has to equal what comes out. Yep. So no cars are created or destroyed in the intersection. Let's call this one C. It looks like x2 plus x3 plus x5 equals 300, right? That one's already set up the way we want it, based on the way the arrows are pointing, right?
Does it matter which order we're doing this in?
No. Nope. The order of the equations doesn't matter because you can swap the rows all day, right? You can swap the rows around the matrix. It doesn't change the solutions. So it doesn't matter. And then the last one, we'll call this D. And it's already set up the way we want it. So D is going to be x4 plus x5 equals 100. So we're going to use these equations to make our matrix, to make our system. So part A says to solve it. So we got to set up our matrix. Or let's just set up, well, yeah, I'll set up the matrix first, because we already have the equations there. Yeah.
I know for like x1, like for A, B, and D, it has the x variables going inward and then the number coming out, and C is the other way around. Well, wouldn't like x1, x3, and x5 be negative, or does that not really matter?
We don't care. If we switched on C, if we switched all these to the other side and made those negative and switched that to the other side, yeah.
We're not trying to zero these out. We're going to leave what they in the augmented part.
Whatever's not there will be a 0. We'll have a coefficient 0.
I
Yep.
mean, like the 100, 300, 600, that'll be for
Yeah, that'll be on the right side. Yep. You want to set it up that way where
you don't want to make this equal 0 like the last one.
the reason I did it on the last one is I had variables on the right instead of constants. Right? We need the constants on the right. We had to move the variables to the left, all the variables to the left, right? And that one just wasn't set up that way, so we had to do it. All right, so our system, the big one, so x1 minus x2 equals 400. So x1 minus 1x2 equals 400. All the other coefficients are 0. B, x1, 0, x2, 1, x3, negative 1, x4, 0, x5 equals 600. Then C, 0, 1, 1, 0, 1 equals 300. And then D is 0, 0, 0, 1, 1, 100. So this is A, B, C, D, right? Those are our equations that we used. Yeah. Does it have to be that way? Yeah. You don't have to have in on the left, out on the right. What you need is what goes in must be equal to what comes out, and you get to decide which side that goes on. It doesn't matter, right? If A equals B, then B equals A, right? So you don't care what order that's in. So you need, I just did it in the order that, where I didn't have to move stuff around later as much as possible. Okay, this one by hand is not bad because you just had a bunch of 1s and 0s, right? If you have a matrix with a bunch of 1s and 0s, it's not bad to row reduce that by hand. I can give you one that's 2 by 2 to take you more time. Okay, so I mean, it's just, you like 1s and 0s. All right, let's call this C. So this is 4 by 6. All right, 4 by 6. Whoops. I'm just going to quickly check that these are correct. That's correct. So I'm going to row reduce. And I get this. That looked terrible. Let's do that again. Some of you like to use graph paper to row reduce your matrices. That's a great idea until you have to squeeze in, 32,000 into a entry, and then it makes it difficult, right? Or squeeze in a big fraction, So I got to where I just didn't use those anymore, and my matrix is kind of curving there. I don't know what happened, but I think we can read it. I hope. All right, so we need to find the leading entries. So we're looking at the rows, right? There and here. So there are my leading ones. So which ones are free?
X3 and X5.
Yeah, X3 and X5. All right, so we'll just do it out here. So X1 will be equal to negative X3, negative X5, plus 700. X2 is negative X3, negative X5, plus 300. X3 is free. X4 is negative X5 plus 100. And X5 is free. So there's my solution. The question just said to solve it, so that's it. We solved it for each X. Yeah, that's just a part, right? Yeah. We got more to do. I'll let everybody catch up if you haven't caught up yet. Okay, so it says find the traffic flow when X3 is 0 and X5 is 100. So this was a part. B part says when X3 is 0 and X5 is 100, find the traffic flow. So we're just going to plug them in, yeah. So X1 will be 0 minus 100 plus 700. What does that give me? 600. X2, 0 minus 100 plus 300, that would be 200. X3 is 0. X4, X5 is 100, so negative 100 plus 100 would be 0. And then X5 would be 100. So that's the traffic flow if X3 is 100, X3 is 0, and X5 is 100. So on part B, it says find the traffic flow when X3 is 0 and X5 is 100. I just plugged those in to each one of these, X3 and X5. Just plugged them in. So this is 0. 0, that's X5 is 100, so I got negative 100 plus 700, be 600. Right? I just plugged them in for X3 and X5. Okay. And then what if they're both 100? Whoops. So we'll start from here. X3 and X5 are 100. So what would be the traffic flow? So 500. 100. And then 0 again. Just some other questions that you could ask, right? So, what's the biggest number that X5 could be? No.
Oh, because you have cannot the other
So if you look at this equation here, X4 is the traffic flow. X4 cannot be negative, right? Well, I guess you could be driving backwards, but no. We're not going to allow negative traffic flow. So the biggest that X5 could be would be 100. That's its max. Okay. Right.
I'll let you ask for X3.
What's the max that X5 could be? That was my question. It's okay. All right. Everybody okay with that? Yeah. Okay. Then we're going to do some chemistry. Come on. This will help you in your chemistry class. Okay? This will help you with your chemistry class. So we're going to balance the following chemical equation. So we have some kind of... Yes, there's water in there. I see water. The great thing is about us, we're not chemists, we're not engineers, we're just mathematicians right now. Okay? You don't care what these things are. Right? You can still balance it. If you understand what you're trying to do, you can still do it. You don't need to understand what the actual chemical process is. I don't know what it is. So we're going to take each molecule and write a vector for it. It's going to be, the vector is going to be how many of each element is in that molecule. Okay? So we're going to start with this one. So Mn is manganese, S is sulfur. But we have to include all the other elements that are in here. So the other elements are arsenic, chromium, oxygen, and hydrogen. Okay? So this guy, we're going to say X1 is how much of it we have, how many grams or whatever, or how many, yeah, whatever, or how many of them, how many molecules we have. We could say that. Just how many molecules we have. We're going to say there's one manganese, one sulfur, 0 arsenic, 0 chromium, 0 oxygen, 0 hydrogen. I need more rows here. So there's my vector for that one molecule. But the thing we have to remember, though, is that this has to stay the same throughout all of our vectors. We have to use the same order. So this is manganese, this is sulfur, this is arsenic, chromium, oxygen, and hydrogen. Okay, we have to keep that same order, even if the order that it gives it to us in is different. Okay, and we're going to say, well, plus X2 is how much we have of the second molecule. Again, I need to go further. Okay, so it does not have any manganese. It doesn't have any sulfur. It has 2 arsenic. That's that 2 next to it. It doesn't have, well, it does. It has 10 chromium. It has 35 oxygen, and it has 0 hydrogen. So that's that one. I'm running out of room quick. X3, 0 manganese, 1 sulfur, 0 arsenic, There's no chromium. There is 4 oxygen and 2 hydrogen. Equals. Right? This is another conservation rule, right? Whatever reaction happens, right? All the matter is accounted for. Okay, so we set them equal. All right, so 1, 0, 0, 0, 4, 1. Yep, I'm out of room. Yes. Thanks. Yeah, it should be X6. Thanks. I got one more. Yeah. H2O. Maybe I can remember that. H2O. All right. For the sake of time, because we're running out of time, I'm going to go ahead and throw this in a matrix. What do we have to do, though? We have to put all our variables on the left. Okay? So what happens is all of these will be negative in my matrix. All of the ones on the right side, I'm going to move them to the left. And I'm going to make them negative, and I'm going to have a column of zeros on the right. Okay? So I've got 7 variables and a column of zeros. That's 8 columns. And I have 6 rows, because each one of these is an equation, right? So 6 rows of elements. I'll just use a, so it's going to be 6 by 8. 1, 0, 0, and then negative 1, 0, 0, 0 on the last one. I think I missed one. Oh, I had another one. Yeah. Okay. 1, 0, 1, 0, 0, negative 3, 0, 0. Whoops. That wasn't right. Let's see.
No, it was a negative 12. No,
There's 212.
I'll check it.
see that 12?
Yeah, I'll fix it. Okay. It's not letting me see the end of that. It's too big. Let's just quickly talk about it. So we get a free variable here. Yes.
If you go below the matrix, it should let you scroll if it's set.
If I go below it,
If you go below it,
Like if you recalculate it and then you did it right, you can get into it. Just don't scroll up.
well, we have a free variable here, and we solve for all x1 through x sub 6. We move this one over, and these are times x7. So if you let x7 be 327, then you'll get that you need 16 manganese, 13 sulfur, 374 arsenic, 16 chromium, and so forth. Okay. I just can't find the rest of it. You don't need a chemistry degree. You don't need that. Just won't let me see it.
Let's just not use that one.
Why not?
Can do RREFA times 2.
It's not working for me. I don't know.